It is now my pleasure to introduce two colleagues of mine, Andreas and Fabian. Andreas Rabenstein has a PhD in physics from the University of Regensburg. He afterwards initially worked as a data analyst and algorithm developer and then joined TNG in 2021. In his client projects, he's working on data platforms and analytics pipelines. And additionally, he's a member of our internal AI research team. Fabian completed his doctorate in discrete mathematics and applied geometry at the Technical University of Munich before switching to IT in 2020 and joining TNG. He's doing a lot of DevOps work, but he also has a strong interest in AI, in particular large language model architectures. He's a member of both our AI research team and our Skynet team, which operates the internal AI server rack. So they will tell you now a lot about distributed training on a B200 cluster. The stage is yours.
Thank you, Alex. And welcome to our talk, Research at TNG. In the next 40 minutes, we will embark on a journey on how to do distributed training on a B200 cluster. But let us start with the why. It's about our own infrastructure. That's because we care about data privacy. If it's the client work, if it's internal research, or the questions our consultants ask to our models on a daily basis. We want to know where the data goes. This is a nice side effect. If you own the hardware, you have to really understand it. Our own research. That's because interesting modern AI topics don't come with a tutorial. There is no answer on Stack Overflow how to keep a train job running on 64 GPUs for several days. Our own results, the models, the data, and especially the knowledge. That's what we do that for. Before we dive right in, we want to introduce ourselves. I'm Andreas Rabenstein. I'm with TNG for almost 5 years now, and I'm a member of the AI research team.
Yes, and I'm Fabian Klemm. I've also been with TNG now for over 6 years. Always also a member of the AI research team, and the research team was founded by our managing partners, Henrik Klages and Robert Dahlke, at the beginning of last year. At this moment also we have currently members Christoph Herb, David Reis, Lars Reimann, Mirko Stabart and Simon Ohler working with us on these research topics. And the AI research team was founded more or less last year around the time when DeepSeek released its R1 model, which was the first open-weight reasoning model. And we would like to show you what we did these days. So this is when we started working on these things. And the first thing what we did is, with these new models, we started deeply looking into them. And we did these kind of brain scans. We call this mixture of tunable experts, because what we did here is, this is kind of a brain scan of a DeepSeek model. It shows kind of which parts of the model are active when you send some input in this. And what we then did, we first did the brain scans, and then also we did some brain surgery and manipulated the model this way a little bit. And then we went further. Oopsie.
The next step we did were the so-called chimera models. What we did there, we used 2 DeepSeek models, namely V3 on the bottom left here and R1 on the top right. V3 is a non-reasoning model. So the inference costs are lower. That means because it's producing less tokens until it gives the user the answer. The R1, on the other hand, is a reasoning model. So the inference costs are higher because it's producing more tokens. On the other hand, due to the reasoning, it has a higher intelligence score. And what we did there, we did some kind of clever merging these 2 models to find a sweet spot here, R1 T2. This R1 T2 model is faster in inference, but smarter in intelligence as V3. And that was quite a success, Fabian, right?
Yes, indeed. That was really successful. So the chimera models were made available via OpenRouter. OpenRouter is an inference API where you can get access to basically any published model in the world, to both the proprietary ones, like the ones of OpenAI or Anthropic, but also most of the open-weight published ones. And here, OpenWeight last year released a sort of ranking of the creators of open-weight models, and ranked by tokens produced, and TNG Tech was on this top 10 list 8th for a certain time spot over November 24 to November 25. And Important to say this is open weight model, so this is why it's not led by OpenAI. Still, though, being ranked as TNG in these names, DeepSeek, OpenAI, Mistral, was of course a tremendous success. Still, though, of course, the TNG colleagues here know this is called coffee by now, and they've heard this so many times they are probably quite annoyed. The question today is what we're doing right now. And today, right now, the research team is working on a distributed 8x8 B200 GPU cluster. We're running our experiments, and so today's talk shall be about showing you how much fun it is to work with such a cluster, how much effort it is, and give you a glimpse of the experiments and stuff we are doing with this cluster. So how did we get there? Why do we have that? So after this great success of Chimera models, of course, last year, naturally, we were under quite some pressure. We still are, and the question was what to do next. What is the next step? And we did a bunch of stuff and soon came to the conclusion the next step will be to go in the direction of more classic training or fine-tuning models. Because these merging techniques that we use to create the Chimera models, they are powerful and they are very resource efficient, but they are limited by construction. So the question was, okay, we would like to go into training and fine-tuning, and with that question immediately, we ask ourselves, how far can we go with the limited resources that TNG have? What is possible? Could TNG maybe even train its own large language model? And this is a question that arises two other questions, which is one, are we skilled enough? We leave that open for today. And the second question, which we clarify maybe today, do we have the resources? And when we talk about resources within TNG, we have to look where we're coming from.
And that's Skynet, basically. Skynet is TNG's internal GPU cluster. And that's also where our research began. But going back to 2023, that was when TNG bought its first single-node GPU cluster. Back then, it was an 8x100 GPU node. It had a total of 640 gigabyte of VRAM. This cluster then rapidly expanded to a heterogeneous multi-node cluster, where we have several terabytes of VRAM nowadays. It's heterogeneous because we have different vendors, we have different types of NVIDIA GPUs. This also laid the foundation for research. So from time to time, we could take some resources of Skynet, do experiments on that. At some point, we even got our own node, which was an 8x AMD MI325X node, which has incredible 2 terabyte of VRAM. And that's something where we could run our first experiments on. But of course, Skynet has to be much more than just bare metal GPUs. You need some software on top of that.
Right. And the main software that we use is our Kubernetes stack. We run a classic Kubernetes cluster on our GPU nodes that orchestrates all our workloads.
Yeah, if you just have plain Kubernetes, you can't assign any GPUs. So you need to install the GPU operator. And this allows then that a workload which you're running in Kubernetes can be assigned to a specific number of GPUs on that node.
But another thing that we learned at Skynet is, although it is fun to work with GPU workloads and the stuff, you still have to take care of the typical maintenance tooling that you need everywhere. So, for example, we have a basic monitoring stack consisting of Floki, Prometheus, Grafana that allows us to monitor all the metrics and logs of both the servers and the applications running there. But naturally, of course, this is not the most important thing. The most important thing, Andreas, is?
That's the inference engine. That's where actually the models run. We usually use VLLM or SGLang and deploy any of these open source models which we then have available. So that's what the user actually is interacting with. He's sending the chat requests and getting responses from that inference engine.
Right, so this is Skynet, and Skynet is where we started last year, where we did our experiments with the Chimera models, where we created those on this AMD machine, and where we also started working at the autumn of last year when we got this new direction to say, okay, now let's go into more the heavy GPU workload stuff with training and fine-tuning. And we asked the question, what can we do there? And also, of course, what do we want to achieve there? And when we talk about what TNG wants to achieve by doing this kind of stuff, we have to be reminded of a kind of the mission of our team of AI research. And there, we want to be honest. So we have like kind of 3 basic goals. And the first goal is naturally, of course, we would love to continue the success story of the Camille model. So if there would be any further chance to adapt or to customize state-of-the-art, really practical models to the benefit both of our consultants and of our clients, that's our major goal. So this is still where we are heading at. Second, however, also very important for TNG is that as TNG Consulting, we want to stay ahead of the AI game and understand what is going on. What are the recent trends in large language models? And we would like to be able to really apply them, to adopt to them, and foremost to verify them. We would not like to rely on just a fancy X post or some published archive paper. We will want to be able to really verify the things that are promised. And finally, yes, as a consulting company, we also want to build up a comprehensive expertise. We want to stand the end-to-end game of AI models, and this means both hardware and software, and this also means both inference and training models. So this is our ambition. And right, so we started autumn last year following this ambition, and we started first experiments on our nice AMD machine and quickly ran into trouble for 2 reasons. The first reason is it's AMD, it's not NVIDIA. This means it's the ROCm library, not the famous CUDA library. And this essentially means that whatever you try, all these latest experimental packages won't probably work out of the box because they are headed at NVIDIA architectures. So this created a lot of headache and overhead for us. And second, we also had to recognize soon that while this machine has an impressive amount of 2 terabyte VRAM, which is impressive for 1 node, this is not that much if you want to really work on state-of-the-art models which have like 500 billion tokens or even over terabyte tokens. So we started dreaming.
Yeah, I mean, it was winter. It was shortly before Christmas, so we were able to dream. We were wandering through the GPU malls of the big vendors, having a look at displaying windows. And in the end, we found it, our dream machine, a 4x8 B200 cluster. So why is that? There would be another 32 B200 GPUs, would give us 5.6 terabyte of VRAM. The connection between the individual GPUs in a node with NVLink is very fast, 14.4 terabyte per second. The inter-node communication via InfiniBand is also quite fast, 400 gigabyte per second. And most important, it's Blackwell architecture, not Hopper architecture. And why is it important, Fabian?
Yeah, so it is actually even more impressive if you compare to what we had. So our colleagues know that when TNG bought its first H100 node, this was a big news. This was like, wow, we have now the state-of-the-art, craziest shit machine running in our basement, and we're really proud of that. But as it is with gaming PCs in former times, nowadays this stuff, it gets old so fast. And then you see these new numbers floating around and you see, wow, Blackwell would mean 2.6 the time of transistors. It would mean 2.4 the times of GPU memory. It would mean 2.4 the times of memory bandwidth. It would mean 2 NVLink speed. It would mean 2.3 times FP8 flops. And all these numbers basically mean it would be way more stronger compute, way faster, bigger bandwidth, and we could do more crazy stuff with that. And
yeah, but don't forget, the most important part why we chose that is native FP4 support.
What do you need that for?
Well, FP4, that's a precision type. That means we just have 4-bit per number. And imagine you have these huge models, hundreds of billions of parameters. Usually they come with 16 or 32 bits of precision per parameter. So you need a huge amount of memory to even fit that on your GPUs. It turns out that you can quantize these models, meaning you can reduce the precision down to even 4-bit per byte, per weight. And that, of course, dramatically reduces your memory footprint. It turns out that for a lot of use cases, this reduced precision is still good enough. So you can save a lot of memory. But, of course, it's not only about memory. It's also about doing computations. So you need to have also fast operations for that FP4 precision. And that's with this native support, exactly that's what's coming here. So what we did, I mean, it was shortly before Christmas, we put that machine on our wish list. We ordered it, and basically we were waiting. We hoped that it would come early, that we can do a setup before Christmas, that we can run our first experiments over the Christmas break. And indeed, Santa came early, so like 1 or 2 weeks earlier than before Christmas. So what we did, we immediately unboxed our package. And then we used the Skynet stack. So we had the stack which we described before. We added Kubernetes, we added the GPU operator, the monitoring. But what we don't need here, I mean, we want to do training. We replaced the inference engine, first of all, with Kubeflow. Kubeflow is an orchestration framework. So you would submit your train job, and then that train job would distribute your workload across different nodes, and it will take care that you can communicate with these nodes.
Second, you need to prepare for your kind of training pipelines. This also means different kind of monitoring. So the classic monitoring with Grafana is not sufficient, and use something like 1B or in our case TensorBoard to live monitor the metrics from the training, such as loss curve, gradient, and so on.
Yeah, and then what you also need is the network operator. This is important because between the nodes we have InfiniBand, and we need to make use of that because with that the communication is way faster. So we had to install the network operator.
Right, and then we had Skynet running, and of course in TNG speed manner we wanted to start the first training as soon as possible to just see is it working. And then there was another big decision to make, and this was essentially which basic training framework to use. And there are the big ones, the 2 big names. The first one is NVIDIA Megatron, which is kind of the industry standard. It's a quite huge library oriented at high performance computing, distributed training. So we thought, yeah, this is a good choice. And then there's also DeepSpeed, also similar in quality by Microsoft.
Yeah, but don't forget about all the other training frameworks. There's TRL, there's Prime Intellect, there's Llama Factory, Ansloth, Colossal AI, and many, many more. So we had to do a decision. And we chose Megatron. Why is that? It's quite mature. It's quite adapted by a lot of companies. Even some training frameworks are based on Megatron. And also, if you have a look at the models which are powered by Megatron, there are quite some companies there, like NVIDIA, Microsoft, Alibaba with the Qwen family, ZAI with GLM. What you have to know about all of these training frameworks, basically they are based on PyTorch. PyTorch is a Python library which allows you to distribute your workloads on GPUs. So essentially, whatever you choose from these training frameworks, in the end, it boils down to running some PyTorch code.
Right, and then after I made this decision, of course, we want to get it running as fast as possible, and then it was really an enthusiastic moment. The first time you see the logs of Megatron popping up successfully, it loads the model. It shows you, for example, here this occasion number of 70 billion parameters in the model. It takes some more time to initialize, and then suddenly the iterations start popping up. It shows you it makes progress, and of course the view automatically goes to the loss, and you see is the loss going down? Is it do anything useful?
Yeah, and of course you don't want to stare at these logs all the time. So obviously you have to monitor your training run. So what you use here is TensorBoard, and what you can see here is the loss curve. So on the x-axis you see the number of steps, on the y-axis you see just the loss, and you see that it's decreasing. That's what you stare at basically when you're running a training. It's not just that curve, you also have a look at like gradient norm, validation loss, learning rate, and many more of these parameters. You try to see how your model is evolving and how it's getting better, hopefully.
Yes, in particular, in order to evaluate whether your model or training is actually working fine, loss is really not enough. So as soon as you start training something, you start evaluation, you start benchmarking. As example, here we see some classic benchmark data sets like HellerSwag, OpenBookQA running against a series of our experiments. So where you consider then each certain checkpoints of your training model and just from there try to understand whether this training goes into the right direction.
And with our full training pipeline, we could do our first research validation. And what we had a look at is the so-called LEMI paper. What they did is they used a very, very small data set, just 78 samples. And what they claim is that they are training a model, fine-tuning it, with that very small data set and that they get a huge performance boost? Well, we tried that as well, and we couldn't verify that. We had a look in the data, and it turns out that their data is very specific to a specific agent harness. So this doesn't generalize very well to anything like open code or Cloud Code.
Right, so we have talked now a lot about training a model. We would like to set kind of common ground what we mean by that. So give a brief introduction. When we talk about training a large language model, what we have in mind is kind of this picture. A large language model consists of layers. Those are kind of neural network structures. And when a model gets an input, it forms this into tokens, and the tokens are then processed layer by layer and produce some kind of output, the next token predicted. And when you in a supervised training setting, this means you have an expected output, so you know what should be coming out, you have what came out. When you have these two things, you can compare them, compute a loss. When you have the loss, you can then so-called backpropagate this and compute the gradient for all of your parameters in your layers. These gradients then in the end give you a delta. With this delta, you update your weights, and this is how you proceed one training step. However, this changes quite substantially when you switch to a distributed setting.
Yeah, exactly. I mean, modern models are very large. We heard that several times, hundreds of billions of parameters. They don't fit on a single GPU, even not a B200. So what you have to do, you have to distribute your model on several GPUs. And then in principle, of course, you do exactly the same. So you do a forward path, but in that case, of course, you have communication between the different GPUs. That's indicated with these blue bubbles here. Then you again get your loss. It's exactly the same loss function as Fabian described before, and you essentially do the same going backward. Again, you have communication between your different GPUs. And that's how, in principle, such a distributed training works. Now the question is, how do you actually distribute it across GPUs? And there are several techniques.
Right, so the first case is when you lack a situation that your model fits either on one GPU or at least on one node, you can do so-called data parallelism. This means that you distribute replicas of your model, full copies of your model to these entities. And then you also split your data set into batches, and then essentially each of these replicas of the model processes one of these batches more or less independently, and you just have to synchronize the loss, and this is how you can perform training.
Yeah, for larger models, one possibility is so-called tensor parallelism. What you do there, you split your models, your layers on multiple GPUs, and then of course you have this communication overhead. But then you have the possibility to fit all the models or the model on your GPUs.
Right, and when you can split a model vertically, of course, the natural next thing would be you can also split it horizontally. So instead of splitting across the layers, you can split between the layers and then have kind of batches of layers in your separate entities, and then you synchronize the output of the one layer batch to the other layer batch.
Another possibility is, especially with new models, you have quite some context lengths. I mean, DeepSeek V4 claims to have or has 1 million context length. That means you can put in 1 million tokens in there. And that's a lot of tokens, a lot of memory. So you can also split the context. You split it in multiple chunks and you distribute in that dimension.
Right. And finally, important to mention, especially in our context, is expert parallelism. This is in the end a kind of special case of tensor parallelism, utilizing the mixture of expert architecture, where your model is natively structured into submodules called experts. And in this case, all your GPUs get a certain subset of these experts and then train them individually. And after each expert layer, you then have to synchronize the states. So typically, you do not choose just one of these parallelism ways. You combine them, always in a way that you attempt to mitigate this enormous communication overhead that you see here by all these blue dots flowing around. And this is how you master distributed training. So to quickly summarize our training stack, we start with our GPU network operators when we start the training, and those assign then the GPUs and also the connectivity devices to our workloads. So we have GPU access and strong connectivity between them. Then we have Kubeflow as an orchestration layer that then spins up our workloads. It spins up pods on each of the nodes and assigns the resources. It also kind of set up the infrastructure and the environment for them. And then therein is PyTorch running, and PyTorch is now doing the actual training and also the synchronization of all these data points that we have seen before. Right, so we mastered distributed training, and time was running fast. Now it has gotten a new year, right? Spring is coming, and of course, with new year, at TNG also, we have New Year's resolutions. And also with the new year of 26, a new frightening word was spreading around in our era. This is GPU poorness. TNG always has been GPU poor, but the whole world is now GPU poor because of this high demand for GPUs, for example, due to agentic use cases, right? And we thought, of course, how could we fight within TNG the GPU poorness? How could we do this? What would be better maybe instead of having a 4-node cluster? Obviously, an 8-node cluster was the solution. So we upgraded our 4-node cluster to an 8-node cluster, and we did this with a certain confidence, because the amazing thing actually around Christmas was when we ordered the cluster, it was running so smoothly, so quickly. Although we had this rather complex infrastructure set up of this distributed cluster, it was running out of the box fine.
Bin ich da schon drin oder was? Ich bin drin. Das ist ja einfach.
Except this time it didn't. So this was we asked us before Christmas, and this time we got the 8 nodes, and it felt like nothing was working. In particular, InfiniBand was just not working. How did we figure that out?
Well, we just started our first training run. That's even a 10 times speed up, and we were waiting for the outputs. Well, yeah, and when you've seen an InfiniBand training run, it's just way faster. So you immediately know something's going wrong with InfiniBand.
Yeah. So this gave us quite some headache. We have talked now again a lot about this InfiniBand. Let's create a common ground. What do we mean by that? What is InfiniBand? So if we have a GPU cluster, let's say we have 2 nodes. Each of the nodes has 8 GPUs each. Then inside each node, those GPUs are connected via so-called NVLink, which is a very fast bus that lets the GPUs inside one node communicate to each other. Now, in order to let the GPUs between the nodes to communicate with each other, you associate, in best case, each of those GPUs with a host channel adapter, and you plug in a fabric, and then the cables go into a switch, because InfiniBand is a switch fabric. And this connects then all the GPUs with each other. You also need some kind of submanager that assigns an address then to each of your GPUs. And over this special network then, the GPUs can communicate to each other in a very fast manner. Except that they didn't, right? So what did we do?
So first of all, we installed Q.toolkit 13.1.
Stupid us, we just forgot the drivers, right? Yeah. Except it didn't work, right?
Yeah. I mean, then we just installed the NVIDIA drivers. You need the latest version, obviously. I mean, should work now, Fabian.
No,
right?
it didn't.
Yeah, I think there's an incompatibility. We should use NVIDIA drivers 580.
Yeah, sure, I told you. Except I think InfiniBand still didn't work, right?
Yeah, there are the Docker OFED drivers. Yeah. Those are the drivers for the HCAs. But now it should work, right?
Yeah, you cannot simply install Docker drivers. I think when we did that, the whole machine went down. We had to reprovision them because they were just not reachable anymore. We totally destroyed the network.
Yeah. Yeah, you have to change the order. Docker first, NVIDIA toolkit, NVIDIA drivers then.
Stupid us. Except I think then still the GPU workloads weren't running anymore.
Yeah, there is the NVIDIA driver server open version.
Yeah, you cannot just simply install any 580 driver. You have to choose the right 580 driver, right? So I think then we had anything set up, right?
At least on the nodes. There was an issue on the InfiniBand switch. So we had to call the data center. And they told us, yeah, the subnet manager is not running. We will have to switch it on.
Oh, yeah. Nice of them. They switched on. Then it was running, right?
Almost. It was running on almost all of the GPUs except for one. So we called the data center again. Well, and they found out the cable wasn't plugged.
Oh, yeah. That's a good thing.
But then in the end, it was working.
It was working. But so this was really a brief story of very stressful weeks we had, and a lot of back and forth, tons of emails with our data center provider until we figured out really the exact same up, the exact really fragile setting in which InfiniBand worked. But then, Andreas, you can show the result.
So now if you compare InfiniBand on the right, not InfiniBand on the left, you immediately see it. It's way faster. So it's really essential to have InfiniBand running.
Right. And so this is where we are right now. This moment, we have this 8-node cluster with a total of 12.3 terabyte of VRAM connected via high-speed InfiniBand, running our extended Skynet stack. This is where we are running our experiments. So we had opened with another question, right? We had opened the question, could TNG now train its own models? Well, maybe let's go one step back here again. What do we mean by train a model? What would this, what does this practically mean? So training a large language model generally consists of 3 main life cycle points. First, pre-training, mid-training, and post-training. Pre-training is like the big part. This is where most of the GPU costs go into. This is so-called next token prediction. Here, your model really learns from an input to predict correctly the right next token. Essentially, that is what we have seen before when we explained training.
Yeah, then usually you go in a mid-training phase. What you do there, you can, for example, extend the context. So how many tokens fit into that model? How many tokens can you feed in there? Another thing which you usually do in that mid-training phase is domain adaptation. So if you're working in a very special domain, like for example a legal domain, you can do some continued pre-training with these domain-specific data, and you can adapt your model to be able to speak in that domain to get some domain knowledge.
All right. And then there's post-training. This is kind of the magic part where your model becomes from a pure completion model, where just able to correctly complete some input into these kind of chat or instruction models that we know nowadays as ChatGPT and all the others. And what you do here are these mostly reinforcement learning methods like reinforcement learning from human feedback or reinforcement learning with verifiable rewards, where your model starts to generate these reasoning capabilities in order to solve complex problems, where your model learns how to do tool calling, very important for agentic use case nowadays. So this is really where you shape the model to be what we nowadays expect as a user from a large language model.
Yeah, and within each of these phases, you have a lot of tasks to do. It's first about data curation. So you need to have a proper data set. It should be high quality. So that's very cumbersome. Then, of course, you can have a look at the loss, but you have to evaluate your model. You have to do some wipe checks. You have to find benchmarks. That's also a hard task because for a pre-training model, you can't just use any reasoning benchmark. It will fail totally. You have to have some easy tasks, maybe multiple choice. On the other hand, you can't use these simple tasks for a fully post-trained model because they will success and you don't measure any difference between the models. So you have to have tailored benchmarks for all of the stages. Then, of course, you have a ton of hyperparameters. Ones related to the training itself, like the learning rate and the learning rate schedule and so on. Then for the model itself, and then also for the parallelization, how do you distribute your model? That's everything which you have to find out what to use. Then, of course, you have to take care about checkpointing and recovery. I mean, we're working in a distributed setup. Everything can go wrong at any time. A GPU might fail. Network might have an issue. So you need to write checkpoints, and you need to be able to resume from these checkpoints. And then, in the end, of course, efficient memory allocation is very important. GPUs are expensive, compute is expensive. So you want to get most out of it, so you have to efficiently distribute your model on your available hardware. So, Fabian, now we have GPUs. We know how to do a training. We are proud we have around 200 GPUs now. Can we actually train a reasonable model ourselves?
Yeah. Well, not surprising, and you all know this inconvenient truth. While we do have now a GPU, TNG, like a few hundred GPUs, well, at least in this area, this is of course nothing compared to the really big players here, like OpenAI, like Anthropic, also DeepSeek, who have those in a bunch of millions, literally. So, to answer this question, could TNG train its own models? Of course, in this sense, when you think of 500 billion parameter models or even a trillion parameter models, then the answer in this setup, of course, must be no, simply because we could not match this kind of compute necessary for that. But what we are always trying to do, or what we are working on, is trying to outsmart that. And this is also what we had done last year. This is what we started with when we worked on mixture of tunable experts. This is what we did when we used assembly of experts to create these career models. This is also what we did now later last year when we created quantized versions of the models, which are extremely faster at a very cheap effort. And many ideas of this kind are laying on the table almost on a daily basis. New ideas pop out on X, on Archive, and a big part of our work, as Andreas explained, is to try them out, to figure out what will be the next step. We have many ideas on the table, and we are trying to put all these together, and this is the way TNG works within AI research. And to kind of close this talk, we would like to show you some illustrations what our daily work looks like.
Yeah, so we've talked a lot about GPU utilization. That's how one of our first training runs looked like in Grafana. So what can you see here? You can see the GPU memory usage. It's quite okay, 160 gigabyte. And then what's very beautiful is the utilization. So all of these 32 GPUs almost have 100% GPU utilization. So that's very nice, and you're very happy once your training run looks like that from a Grafana perspective.
Yeah. And another important truth to tell is, and maybe important to calm down some colleagues here, we're not just spending the money for 8 nodes just for some research experiments. No, these nodes are mainly also there to serve our consultants with inference. So we have a kind of dual use here, and we try to focus during daytimes for working hours to serve on these nodes inference for mostly agentic use cases right now to our consultants. To be able to use them. And then in the nights and weekends, we can then more focus on research workloads.
Yeah, then of course fine-tuning is way more than just starting a script. I mean, we have all these issues with the infrastructure itself, but then you run your script, you get some loss curve, but it's way more. I mean, we are looking, you have a model which is really big, so you have a huge amount of numbers, you modify all of them, and then you want to find out, what did my model actually learn? Did it learn the correct things? Did it just learn to do some weird stuff and so on? So you really have to have a look at these numbers itself. And you can imagine it's like a huge dimensional space. So we have found some visualizations how to visualize these weights, the changes in the weights. And you're staring at stuff like that here, and you try to find some patterns out of that.
Right. And as soon as you, of course, start with working with such complex systems as large language models are, you run into the typical errors, misbehaviors. You get one behavior during training, and then you deploy your model using VLM, and you get a total different behavior, and then you start debugging. And this is one example where we really had to debug on a token level to compare activations between Megatron and between our VLM to figure out some kind of gap that we observed that we just could not explain till we had spent, I think, one colleague of us a week on this issue.
And we are not only interested in fine-tuning, of course. We are also interested in model performance optimization. Performance in that sense means speed, so really that you get more output out of your model. And what we tried, for example, here is we used our Chimera model, and we implanted the sparse attention from DeepSeek v3 into that model, because sparse attention is faster, and we can indeed see that here in that throughput graph. We also have similar graphs for quantization and so on, so that's also part of our daily work.
And of course, experiments, as many as we can conduct. For example, here, one example conducted by our colleagues Simon and Mirko, who looked into the so-called NMOE or Numina MOE approach, where the authors claimed they had found a very high efficient way to mitigate this big communication overhead when you use expert parallelism. And this is kind of a typical result that you get then. You get that in some configurations, especially their configurations, it works very well. It is very impressive, although we figured out that for our standard setups, it is not that beneficial that we would really wanted to adopt that.
Yeah, so what are our key takeaways? State-of-the-art GPU hardware is fun. So whenever you have the chance to play around with it, do it, use it, but it's also very tricky, so you will spend a lot of time there. Infrastructure is really the silent killer. I mean, we showed you the InfiniBand story. we could share some more stories like that, where you really take way more time than you expect. And one tip, start simple. So do that what you know is working, and then scale that work up. With that, we want to thank you for your attention, and we're looking forward to your questions.
Thank you.
Thank you very much for the excellent talk. And I already see the first question.
Yeah, thanks for the talk. Very interesting. I mean, you're obviously facing somewhat of an uphill battle, right? You have limited resources, you have high energy costs, you have European regulation.
Yeah.
Is this really to see how much can we do, how intelligently with how little, or where are you going with this? What's the objective? Is it just trying to create new models, new ideas? Is it really basic research to see where it can be applied? And also considering the fact that once you do publish it, others will probably copy it within a fairly short time.
So I would say no, our main ambition is not to create new models because this would be illusional. We would like to be able to do as much as we can with our resources, which is in this field of the chimera models or in this field of adapting models, making them better, making them more appropriate for our clients. This is like the dream thing. And still, though, also why we are investing this as much, although I'm maybe not like not a managing partner, I'm not the one to comment on this level. But from my perspective, as an engineer, I would say the AI race is still open, which is interesting. So like 2 years ago, it was unclear really in 24 whether like the big players like OpenAI for most of this time would just make the race and all others just have to use their solution because there is no workaround. And this is why this R1 release was such a tremendous cut historically, because this was the time when it was kind of made clear that no, at least now still open weight models have still a real chance, and we at TNG use open weight models. We use mostly like right now GLM for our coding agents, for as example. So open weight is still going on, and as long as open weight is going on, we can play a role there, and especially also Europe. You are right, the regulations are from our perspective an issue, at least a challenge. Let's put it this way. But we also see that in Europe the AI race is not done. And yes, TNG, let's say at least we want to have our head up here.
All right, next question from over here.
Hello, thank you for your presentation. It was very interesting. I have a question about the cluster and if you're experiencing there are any hardware failures also, for example, GPU failures so far, and if yes, how often that happens?
Sorry.
Yeah, we from time to time have something. Yeah, they had issues with the cooling, for example. They got a small hole in the cooling system. And yeah, it took us quite some time to communicate with them. So we have had this machine now left for like a couple of weeks.
We got it back yesterday.
Yeah, we got it back yesterday.
I got it running again.
Yeah, okay, so it's running again now. So we have these issues. But actually during the trainings runs, that wasn't that much of an issue that we had to recover from GPU failures.
But from time to time you see that there's mechanics behind this, and if a valve breaks and like leaks water in your cooling system, yeah, this is an issue.
More questions in the audience?
How did your research pace changed since you are you using more AI tooling, and how does it affect like the research pace? Thanks for the great talk, of course.
Yeah, thank you. Yeah, it definitely changes. I mean, coding stuff is way easier. If you want to have a visualization, we often change from having static plots to have just complete Streamlit apps or something like that, which are already interactive. So you can much faster look at the data, which is also a big part of that. And if you just have an idea, I mean, you can't just wipe code it. And then you do some verification tests on that. So that definitely changed.
Yeah, I would agree. It changed because we're capable to change. And also, what changed with especially this cluster for us now is that there's another kind of awareness, even now that we if we not utilize this, especially at the night, for example, we have high opportunity costs, and we are still a business-oriented company. Of course, at TNG, we do not do this for the sake of goodwill, the research. We want to do this for a business case at the end, somehow. And so whenever our GPUs are not utilized, it's kind of our fault, and we should take care of that, because then we're not utilizing what we're paying for. So we had to change the pace. Yeah, it's a good question.
More questions? If not, I have one. It's still a while until next Christmas, but what's on your wish list right now?
Ask Henrik.
I mean, getting bigger is always better if you're working with research. But to be honest, I mean, it's also quite expensive, those machines. So you really have to think about your investments.
And I would say last question from over here.
Is it, so you showed this chart with the comparison from OpenAI to your cluster. Is it a wrong understanding if you could say that you just kind of train, for example, then 50 times as long that you could still train it, or is this not feasible? So is this understanding wrong that you could theoretically kind of like swapping or something like that?
It's just the factor 50 is wrong, that's the issue, yes.
Yeah.
You have some years.
50?
It's more like 10,000, the factor. But yeah, in principle, I mean, there are two things. If you fit your model in your GPUs, which would work out, I mean, then it would be the same factor in time, essentially. So you're right, basically, that if my model fits on my available GPUs, I can just train it longer. Because, I mean, it's just parallelization in the end. And you can either do it in parallel or do it one after the other. Yeah. But you can't compete in that race, obviously. I mean, it's a factor of 10,000.
And it is a very good point, because like part of why we really kind of are now way better off with this distributed setup compared to our first setup with one AMD node is because indeed you need some basic ground, and this is nowadays a few terabyte VRAM that you can just fit an essential training on it, which we can now on these 4 or 8 nodes, whatever we're using at the moment. It could, yeah, this is now possible. And indeed, this opens this theoretical approach. Of course, we'll not proceed this because of the factor 10,000, but indeed, this is like where we can play around now.
All right. Thanks again for the great talk. I guess you'll be around for questions afterwards as well.